The mechanics of Earth's natural climate cycles. Earth's long-term climate history is defined by predictable astronomical variations that dictate the rhythm of our planet's temperature and glacial expansion. Understanding these patterns is essential for distinguishing between the slow, natural shifts that have occurred over millions of years and the rapid, human-induced changes observed in the modern era. By studying these celestial mechanics, researchers can reconstruct ancient environments and better comprehend the sensitivity of our current global climate system. The Milankovitch framework. At the heart of Earth's long-term climate variability are the Milankovitch cycles, a set of three distinct orbital parameters that determine how much solar energy, or insolation, reaches the surface. These cycles operate on timescales ranging from tens of thousands to over 100,000 years. They serve as the primary pacing mechanism for the transition between expansive ice ages and the more temperate interglacial periods we experience today. Eccentricity. This cycle refers to the gradual shift in the shape of Earth's orbit around the Sun, fluctuating between a near-perfect circle and a slightly elongated ellipse. When the orbit is more elliptical, the distance between the Earth and the Sun varies significantly throughout the year, which directly impacts the intensity of the solar radiation received at different times. Obliquity, often described as the tilt of the Earth's axis, this cycle influences the angle at which sunlight hits the hemispheres. A greater tilt amplifies the extremes of the seasons, leading to hotter summers and colder winters, while a lesser tilt results in more moderate seasonal transitions, often preventing the total melting of high-latitude ice sheets. Precession, this is the wobble of the Earth on its axis, similar to a spinning top slowing down. Precession determines the timing of the seasons in relation to the Earth's proximity to the Sun, shifting whether a hemisphere experiences summer when the planet is at its closest point to the Sun, or its furthest. Amplification through feedback loops. The energy changes introduced by Milankovitch cycles are rarely strong enough on their own to trigger a full-scale glaciation or a major warming event. Instead, they act as a pacemaker that initiates secondary, more powerful feedback loops within the Earth system. These feedbacks are the mechanisms that significantly amplify small initial changes in solar energy, turning a minor drop in temperature into a massive multi-millennial ice age. The albedo effect, as temperatures begin to cool due to orbital shifts, snow and sea ice cover expand across the poles and higher latitudes. Because ice and snow are highly reflective, they bounce more sunlight back into space, a property known as high albedo, which further cools the planet and encourages even more ice growth. Greenhouse gas regulation. Natural climate cycles are closely tied to the chemical composition of the atmosphere, particularly carbon dioxide levels. When the oceans cool, they become more efficient at absorbing carbon dioxide from the atmosphere, which lowers the greenhouse effect and accelerates cooling. Conversely, as the planet warms, these gases are released back into the atmosphere, creating a warming feedback loop, short-term variability, and solar influence. While orbital mechanics set the long-term stage, other processes introduce fluctuations on much shorter, more immediate timescales. These cycles are vital for understanding regional weather patterns and decadal climate variability. They highlight that climate is not a static state, but a dynamic system responding to various internal and external pressures. Solar activity cycles. The sun is not a constant light source. It undergoes an 11-year cycle of magnetic activity during which its brightness fluctuates. Additionally, there are longer-term periods known as grand solar minima, during which the sun exhibits significantly reduced activity for decades, potentially leading to cooler periods on Earth. Ocean-atmosphere interaction cycles like the El Niño to Southern Oscillation are prime examples of internal climate variability. By shifting the temperature of massive surface areas in the tropical Pacific, these events can alter atmospheric circulation and global rainfall patterns, leading to short-lived spikes or dips in global average surface temperatures. The modern climate context. As of March 2026, scientific consensus underscores a vital distinction. While natural cycles provided the template for Earth's climate for millions of years, the current rate of warming deviates sharply from these historical norms. The speed at which temperatures are rising today exceeds the pace of Milankovitch-driven shifts by orders of magnitude. Modern data indicates that while the planet remains susceptible to natural influences like solar variability, these forces are now being heavily overshadowed by human-driven emissions. Understanding the natural background cycles is not just an exercise in historical geology, it is a fundamental requirement for assessing the current state of the climate. By isolating the slow rhythmic pulses of the Milankovitch cycles, researchers can clearly see that the modern warming trend is an outlier in the context of the last several 100,000 years. To navigate the future, we must synthesize our knowledge of long-term natural variability with our observations of present-day changes. The interaction between astronomical forcing and human-influenced atmospheric composition creates a complex, evolving landscape. By continuing to monitor these systems, we gain the clarity needed to identify the human fingerprint on the climate, separating the background noise of natural orbits from the acute signal of modern industrial impact. In summary, Earth's climate is the product of a complex interplay between slow, predictable orbital shifts and rapid interactive feedback mechanisms. The Milankovitch cycles drive the long-term march of glacial ages, while solar and oceanic cycles add layers of shorter-term complexity. While these natural drivers have historically shaped the planet, current research highlights that modern climate change is occurring at a rate far exceeding these geological norms, emphasizing the necessity of understanding these cycles to accurately measure our current environmental impact, getting rid of outliers that don't fit with real-world data. Getting to know equilibrium climate sensitivity. Equilibrium climate sensitivity is a key way to measure how greenhouse gas levels affect the global mean temperature over time. This temperature benchmark shows how much the climate system will warm up after it is fully adjusted to a doubling of atmospheric carbon dioxide. This includes the complex dynamics of the deep oceans and different atmospheric feedback loops. ECS gives scientists and policymakers a very important tool for setting global environmental goals and figuring out how long human climate interventions will last. It does this by setting a theoretical limit on how much the temperature can rise, the changing nature of atmospheric feedbacks. It is not always easy to figure out ECEs because there are so many internal feedbacks that either make the initial warming effect stronger or weaker. As the atmosphere warms, it changes how clouds are spread out and how thick they are, how much sea ice there is, and how much water vapor is in the air. These secondary responses make the modeling process a lot harder. Uncertainties about cloud feedback, these are the main reason why current climate models don't agree with each other. Clouds can either reflect sunlight coming in or trap thermal radiation going out, which makes them a complicated variable that scientists are still trying to pin down with perfect accuracy. Oceanic thermal inertia, the oceans are so big and deep that they can hold a lot of heat, so it doesn't reach equilibrium right away. ECS is different from metrics that measure short-term responses because this process can take hundreds or even thousands of years. Ways to make things louder, positive feedback loops like the melting of polar ice caps that lower the planet's albedo, speed up the warming process more than just the heat-trapping effects of carbon dioxide. Differentiating ECS from transient climate response. Students of climatology need to be able to tell the difference between ECS and transient climate response. ECS shows the final settled temperature after the whole planet has fully reacted to a doubling of greenhouse gases. TCR, on the other hand, shows the temperature change right after those concentrations double. TCR looks at the warming that happens in the short term, when the atmosphere is still changing. Systemic equilibrium, ECS takes into account the fact that the deep ocean takes longer to absorb heat. This is because the deep ocean is a huge thermal reservoir that eventually catches up to the warming of the atmosphere. Policy implications, TCR is often seen as more important for making quick decisions about cutting emissions because it shows how much the Earth has warmed during the transition. ECS, on the other hand, helps us understand the long-term permanent effects of our atmospheric footprint. Ways to figure out sensitivity. Researchers use a triangulation of different data sources, each giving a different view on how external forcing affects the Earth's climate, to get a rough idea of what ECS is worth. The scientific community is trying to narrow down the range of uncertainty and make clearer predictions for the next few decades by cross-referencing these methods. Historical climate observation. This method looks at temperature records from the industrial era to now and compares them to the rise in greenhouse gas levels caused by humans since the mid-19th century. Paleoclimatic reconstruction. Scientists look at geological proxies like ice cores, tree rings, and ocean sediment to figure out how the climate reacted to changes in atmospheric carbon dioxide millions of years ago. This gives us a long-term view of how sensitive the climate is. Researchers use high-performance computing to create advanced Earth system models that can predict how the atmosphere, cryosphere, and hydrosphere will interact in the future under different emissions scenarios. Changes in scientific predictions. The history of ECS estimation shows that the range of possible outcomes has gotten much smaller. Previous research faced significant challenges due to a plethora of possibilities, some of which were physically implausible. By carefully looking at the evidence and getting rid of outliers that don't fit with real-world data, modern reports, especially those from the Intergovernmental Panel on Climate Change, have come to a more solid and focused conclusion about how sensitive our climate system really is. Nevertheless, recent advancements in the sixth phase of the Coupled Model Intercomparison Project have yielded new data points. Some of the newest high-resolution models have come up with ECS estimates that are closer to the higher end of the range that was previously thought to be correct. This has led to a lot of heated scientific debate about whether these models are more accurately reflecting reality, or if they are overestimating certain atmospheric sensitivities. The standard for checking these high-end projections is to keep comparing these modern simulations to paleoclimate records. The role of ECS in global climate management. ECS is like the North Star for carbon budgeting in the context of international climate policy, like the limits set by the Paris Agreement. We need to get to net zero emissions much faster if the climate system is very sensitive in order to stay within temperature limits. On the other hand, a lower sensitivity could mean that there is a slightly wider window for mitigation efforts. The uncertainty surrounding ECS is not just an academic issue. It is also a direct cause of the urgency felt by world leaders because the effects of human-caused warming are so serious. The accuracy of these measurements has direct effects on carbon emission budgets, figuring out how many tons of carbon can still be released before certain global temperature limits are reached. Risk assessment models give the insurance industry and governments the information they need to get ready for the changes in weather patterns and sea level rise that will happen because of climate change. Public communication, breaking down complicated physics into useful information for people who need to weigh the pros and cons of economic growth and protecting the environment. Summary and main points. In conclusion, equilibrium climate sensitivity is still an important but complicated measure in climate science. By measuring the Earth's total steady state response to carbon dioxide forcing, it helps us understand the long-term effects of global climate policy. Even though there are still some unknowns, mostly because of how clouds move, we are getting a better understanding of the past as we move toward more accurate historical data, better paleoclimate research, and more advanced computer modeling. Anyone who works with climate data needs to know the difference between short-term warming and long-term equilibrium. Ultimately, the continuous improvement of these values connects the abstract physics of the atmosphere with the concrete essential policies needed to protect the planet's climate for future generations in a world that is getting hotter.